It's a really easy question.
I think what we're talking about is what's at the very edge.
Hello and welcome to the Edge Tech Podcast. I'm David Kosloski. Alongside me today, I have got Mr. Steve Savage, the Chief Operating Officer at SNUC. Steve, thanks for being here.
Thanks, David.
And Chuck Abdouch. I'm going to butcher that name forever. It's the CTO at SNUC. Thanks for being here, Chuck.
Thank you.
Awesome. So today we're talking about compute power in harsh environments. And really, let's kind of set the scene. I want to touch on what are some of the most harsh environments that compute has to be. And I'm going to keep it very open-ended. I just kind of want to hear what your thoughts are.
The challenges I've seen in the past is steel mills. Steel mills, the computers that are inside your office, these customers were buying new computers every 6 months because the chemicals in the air actually corrode copper. And then the same as with pig farms. Pig farms is like 3 months for a computer to last. So the caustic fumes that are in the air actually will end the life of a computer pretty quick. You have drill heads where you have an explosive environment.
Real quick, I'm going to interrupt you. So corroding, how do you fix that?
You seal the computer.
And what do you seal it with?
So we actually build computer inside of a fully enclosed chassis with neoprene gaskets, usually double gaskets. You can also nitrogen fill the environment under pressure. So if there's ever a leak, you're leaking air out instead of getting fumes in. In explosive environments, these are NEC 505, 506, like at a wellhead or in a petrochemical plant, because you got lots of computers. Those computers can't cause sparks. And so on those, we actually have a gas channel where you want to equalize the pressure inside and outside of the sealed computer, but it goes through this really long, wavy tube so that a spark can't make it all the way from the inside out.
And pig farms, what?
Oh, man.
What am I missing there?
The nitrates that come out of their manure just corrodes everything.
Interesting. So how do you fix that? Same way?
We also do a coating. So we do a coating on the motherboard. So if any of the fumes get to the motherboard, that they'll have a coating to go through. It could be a wax coating. Nowadays, we actually use a nano coating that has a tighter bond than wax. In the old days, you might remember the old Japanese radios that were dipped in wax.
Yeah.
And so that would be something the old So yeah, you used to get motherboards and they'd have this wax coating on them. And that was to keep any fumes from getting to them, might corrode them.
Got it.
And now, so we put them inside sealed environments. We can pressurize them, and then we can also coat them so that should any of these other barriers fail, that you get to the final one. Now, most customers who are buying computers for this environment, they would be surprised if they got 6 months of use out of a computer.
Jeez, even with the coatings. And
right. So if you can give them a couple of years, they're gonna keep coming back for those systems.
I want to go one for one here. Steve, do you have any?
Sure. So I think a couple of practical use cases are, say, like in backpacks or wearable technology, right? Where folks are needing to have wearable technology, either from a civilian standpoint or in a military type application, where they need to travel out into the field with some kind of technology.
Yeah.
Maybe in a Humvee, where they're driving through deserts or environments they're not typically using standard IT. You need ruggedization for that. And then some are one application we worked on was a missile launch system. So as that's launching missiles, there's a lot of shock and vibration and temperature, and they're not in the best environments, right? So there's a lot of different applications like that where you have to take into account not only just the water or the weather or the temperature, but also the environment as far as, shaking and vibration. And there's a lot to the...
And the vibrations are affecting like screws coming loose, et cetera.
Exactly.
Which is ironic because rumor mill has it that earlier today, you also maybe needed a computer that was a little bit more ruggedized as you were doing donuts in a parking lot, from what I was told.
We'll see what comes out on that. There's no evidence as
Right, if there's no video, it didn't happen.
Yeah. Great. So, do you have any more examples that you guys want to touch on?
Some other examples. One of the most challenging, I've talked to two customers on this. We're actually working with one, is space. we actually have a computer in space. Now, when we talk about computers in space, like laptops that are in the ISS, those have to be rebooted 2 or 3 times a day because gamma particles will come in and hit a memory cell and flip it, and the computer will lock up and they have to reboot them. You can't do that when you're in a satellite. And so we're working with companies on how we can harden them to a level that it can survive being in a satellite. And so in those cases, they typically want to run 2 or 3 computers in a cluster. And so if one of them gets hit, they can reboot through the BMC. They can reboot over a signal. They can reboot that one that failed, bring it back online, get it synced up with the other 2, and get back into triple redundancy.
When you're talking about the erosion and things getting into this wax coating, is that not solved by sealing it? Like
you can seal it, and then sometimes you get into that the neoprene is typically what's used. That sometimes things get through the neoprene.
I mean, even like I'm saying, remove fans, or is it still going to get through? Like if you removed a fan, you did a fanless system, would that solve it?
Well, that's what we're talking about.
Neoprene.
So what we're talking about, because you have to have a seal, you have to have an opening where you put the computer and electronics in there, and then you have a double neoprene gasket, and then you bolt the thing together. And all of your connections, and this works the same for watertight connections for equipment that's outdoors or even underwater, where all of your connectors are watertight connectors. And so they displace water as typically you would attach them outside of water, and then they would have a sealed coating. And so then they can go underwater. But there are connectors, like if you need a connection to be made and broken while submerged, those connectors exist. And most of these connectors are pretty expensive and pretty big. And so when you're talking about talking about a small computer, and then you add this capability, you typically grow the size maybe 200%.
Yeah.
But you started off with a fairly small computer, so you still end up with a smaller solution than people are used to.
And there's still ways to help with that too, to minimize some of the cost and the size as well with a conformal coating. So there's a product, or multiple products nowadays that you can dip the electronics in that'll puts a coating over the device, kind of like the wax you're talking about, but not so obvious. That'll help protect it from the environment as well. So you could run it in water, submerge it in water, even without those connectors.
Yeah,
as well.
So with the nano coating that we have, you can actually take the motherboard, plug the RAM SSD in it, dip it in the nano coating, dry it, and within 2 minutes, submerge it underwater and it's fully operational.
Crazy. I have a question that I want to get to of like different environments and the solutions that maybe are around it. But before I get to that, I want to ask, is there the most optimum ideal environment for a computer? Like the best protocol, like it's 70 degrees, this type of humidity.
10 degrees.
10 degrees?
Well, 10C. So
10C.
like 40 degrees.
Okay. That is the best temp. What about like humidity, any of these other?
You don't want condensation, but other than that, it doesn't matter.
So you just leave it running.
Yeah, and
don't
leave it running, move it.
Turn it on and off.
Oh, really?
Just let it.
So just keep it run forever.
Run it.
That's interesting. Okay. And so keep it running, 10 degrees Celsius, about 40 degrees Fahrenheit, and then zero humidity, the lowest humidity possible.
No, it could be 50% humidity as long as it's not condensing on where you're getting water.
Sure. And then don't let it move. Just let it sit.
Yeah.
Yeah. All right. Fair enough. That will make your computer.
And then lead shielded, you won't get, gamma radiation, because gamma particles they come down and they hit things on Earth too. So if you lead line it, then you protect it from gamma particles, and you might not ever see that computer fail.
So the next gaming rig, I have to put a lead case around it, right? And then I'll be good. Fair enough. All right. So getting into, let's say, the extreme cold, what are the things that you're thinking about when you're building a computer when it's in the extreme cold situation?
Crystals. So computers have clocks. They have timing circuits. And typically the timing circuits have a piece of mica or quartz crystal that vibrates and gives you your clock. When you get to about -10, those crystals get very fragile. And then you turn the computer on, it starts vibrating and they crack. And so in the past, our computers don't have these. But in the past, what I would have to do is get a version that had a heater built in. Literally in the small, tiny part, there's a resistive heater, and I have to turn the heater on, heat the part up before I start trying to vibrate the crystal or it would crack on me. Nowadays, we typically use caps and resistors, which are very stable. They do change with temperature, but they won't break. And then we take their vibration and we compare it to kind of what it should be, and we adjust it. And that's all done inside the computer chip. And so nowadays, we can go colder. If you wanted to do like minus 100, I would still start with the heater solution.
C or Fahrenheit?
I'm not sure it matters.
Point. Fair enough.
And some of the consideration there also is, are you talking about firing up the unit, the device, once you're at say a negative 40? Or are you going to have the device running and then move it into an environment, right? So some of those, from a design standpoint, you'd want to take into consideration the use case and how they're going to interact with the device and how they're going to, when and where they're going to power the device.
Yeah.
There's much different design considerations if you're going to take a device that's already running and run it into a lower temperature environment as opposed to, starting it fresh at a negative 40.
And an example of that might be a lighting, something that's mounted on a light pole at an intersection up in Minneapolis, right? It could be somewhere in the summer, it could be minus 50 in the winter, right? And so if it's sitting there running, it can generate enough heat to keep itself comfortable, but because you're having to keep it cool, you probably put some louvers and allowed airflow through it. And by allowing airflow through it, now it's too cold, you need to close those louvers. So you kind of need a temperature management system for your box so that, and it's not just the computer, you have other controllers running the cameras or the traffic lights. And so by providing a kind of a nice environment for all your electronics, you can get more life, right?
Yeah. Fair.
Chuck brings up a good point, which is sometimes people are trying to ruggedize a device when really they'd be better off putting a ruggedized box out there and just embedding a normal device inside that box that creates an environment that'll support the IT.
Yeah. Why?
So there's multiple ways to solve that problem.
I was going to say, would that not be the first most economical approach?
Well, you might have space constraints, right? It'd definitely be the most economical approach, but you could have space constraints. You might have aesthetics, right? So there could be practical reasons why that wouldn't be a good solution. But a lot of times, I think people are trying to ruggedize a device when they'd be better off putting it in a ruggedized box or container.
Right. Yeah, it's like the voice of reason in the situation.
Yeah.
Let's not make this overly complicated. Let's put it in something that's a little bit cheaper. All right. One more. Let's shoot to extreme heat. What are you thinking about when extreme? You said crystals for the cold. What do you think about for heat?
Heat reduces the life of electronics. But as far as the temperature, we have a lot of customers that say, can we get to 85C? That's like 180 degrees. What place on earth are you running a computer that the environment is 180 degrees?
A sauna.
Right. Well, but the computer doesn't have to be in the sauna. The sensors could be in there.
Sure. Yeah, that's fair.
So when we talk about realistic, that we need 125 degrees, that's very doable. 125 F, right? That we're down at about 70 C. Oh, that's easy to do. We can provide solutions that can handle Death Valley midday, right? And still operate. Now, electronics in itself ages with heat. So if you want, what we used to do to find out how long a computer would run is we'd run it in an environment chamber and run these hot, cold cycles and age it. And we would age stuff maybe 2 or 3 years and it would fail, right? And so we could guarantee, hey, this is going to run for 2 years and this is a bad environment.
Sure. And then last one I think I can go with is, maybe there might be 2 more, but what about water? Underwater, like computers sensors that are underwater, like and then my assumption is based off the limited knowledge that I've gotten about IP ratings from one of our conversations would be, there's like a 9, is that correct? Or is it, there's 7, 9, I think, I'm not too sure.
6, 8.
6, 8, okay.
6, 8. Typically when you say ingress protection, IP is ingress protection. 6 means related to water. And then 7 means it's submerged. When you say 8, you're meaning it's submerged to some depth. So you typically say what the depth is, like 10 meters or 1 fathom. And so we test to like 1 fathom, which is 33 feet down, right? And there's also a 69K rating, which is kind of just saying it's extreme. And it goes back to the same things that we coat the boards, then we put them inside of sealed boxes, and we use watertight connections, and we can pressurize air inside of them. So while they have a lot of external pressure on them, let's say your fathom is 14 PSI, right? That inside we've actually pressurized it to 14 PSI. And so now it sees the pressure equal and it doesn't want water to come in.
Would there ever be a situation where a compute needs to be at the bottom of the seafloor?
Sure.
Sure.
Yeah, if it's on an internet cable, right?
Yep.
Or you're using it as a transceiver or something.
So what is that IP? Because you said 30 meters or 30 feet. I can't remember. And
Well, with that one, they would just specify that it has to be whatever the depth is. And that stuff is very expensive, and it's through several layers. So it's not like a computer that you look down there, oh, I see this fanless computer on the seafloor. You see a massive box and through several layers.
Yeah. The situation we were talking about before. Okay, got it. Fair enough. And in a situation, you're not building computers, you're working for a company and they say, hey, we are going to space, or we're going to work in Antarctica. What is it, the key elements for the job? What are you typically looking for? And I'm using all the factors. I'm sure we're talking about IP, but like, what are all the things you're looking at of like, it's got to be the best chassis. It's got to have, the coating you're talking about.
You want to start that one or?
Go ahead.
So the first thing is how you're handling the environment. Working for a petrochemical, or doing a design for a petrochemical company that was going to set off explosives in the Arctic and then look at the reflections and find oil. They came in and said, hey, we need to survive minus 70, right? And I said, where's the computer? Well, the computer's inside the vehicle. Well, how cold is the vehicle? And they said, well, it's minus 70 when it's sitting out there. And I go, and you all get in it and you don't have heaters? Oh, no, we get in. We turn the heaters on and we get it nice and toasty warm. And I said, before you turn the computers on? Oh, yeah, we don't turn okay, so you don't really need the computers to work at minus 70, minus 10, or even 0. And they go, oh, yeah, we always get up to about 4 or 5 C before we would power everything up because nothing survives that. Okay, there's your answer is warm up the environment and then you don't need the solution, right? But if it's outside on a traffic pole or something, you need the solution. Yeah. So what we work with the customers, what kind of space do you have? Can we solve the problem cheaper using the enclosure for the equipment? Mm-hmm. Because this provides protection for your other equipment. Mm-hmm. And in some cases, they've already mitigated that and they get down. We also can provide the computers for sealed environments. And this is a very, and I'll tell you how we do it is normally you have a computer, let's say fanless computer, it's generating heat and you're inside of a metal box, and you got to get that heat out. Well, we have a heat sink that goes on our computers that allows you to mount it to the inside of the box. So now it's radiating the heat into the structure. So now you're not heating up the inside of the box where you have to figure out a solution how to vent that heat, but you're heating the box itself. Well, what do I do if it's in Phoenix? You can take a heat sink and just kind of stick it on the outside of this metal box lined up with the internal heat sink and radiate more.
Sometimes the most practical solution ends up being the most economical too for your customers, which is great.
And we have customers that use that. Primarily, we have 2 race car companies that have computers on their race cars collecting a lot of telemetry. And so I know on one of them, we're in the air scoop for the carburetor. So as the air comes in the scoop to go down to the engine, the computer is flush and has a little bit of a heat sink in that airflow.
Crazy.
Whenever we look at these environments, and when we engage with a customer to understand, what we need to design for, we're going to look at what's the power conditioning, what kind of power, where are we getting the power from, how good is the power, where's it going to be mounted, what kind of mounting options do we have, if it's in enclosures, is there air moving, are there vents, what's the outside temperature, is there water involved? So kind of looking at all aspects of the design to see, are there ways that, considerations we need to be thinking about as we look at how to design, for that. So a lot of it's kind of understanding the use case and exactly where they're going to mount it and the way that they're going to power and what they're going to drive with it.
No, that's great. Guys, I really appreciate you taking the time to talk today about, compute and harsh environments. And thank you for listening in to the Edge Tech Podcast. Again, I'm David Kosloski. If you like this episode, please make sure to like, share, subscribe. Take care.